Now, this is in continuation to our previous video lecture, wherein we were understanding the packaging efficiency, right? We are done with the packaging efficiency of simple cubic and face-centered cubic in previous video lecture. And we found that the face-centered cubic structure occupies, in face-centered cubic structure, the packaging efficiency was 74%, right? And CCP, which is cubical closed packing, and hexagon closed packing, both have packaging efficiency 74%. We have done this in previous lecture. Now the last that was left was BCC, body centered cubic, right? In body, let's see what is the packaging efficiency now in body centered cubic. How much space is occupied by particles in body centered cubic, right? Now let's first see the number of particles in body centered cubic. Sorry. Number of particles we already know, it's 2. Right, now let's just recall how we calculated it. That will make our understanding better. Right, this is a cube, right? And in body centered cubic we have particles at the corners, 8 corners of the cube, and there is one particle at the center, right, which is not shared by any other unit cell, and this particle, one particle at the center, belongs to this unit cell only, right? So now if we draw a triangle like this, if we join these 2 points, right, and join these particles, right, and if you look at this, we have 2 triangles now, this triangle and this triangle, right? Now this is your A, this is your B, this is your C, right? Now here, this is D, say this is D. We have 2 diagonals. One is the face diagonal, this is the face of the cube, and the diagonal in the face is your face diagonal. AC is equals to face diagonal, and this AD is your body center diagonal. We call it a body diagonal, not body center diagonal. This diagonal AD, which is passing through the center of the cube, is your body diagonal, right? And we know packing efficiency is space occupied by these particles at the corners and the particle at the center, space occupied by these particles in this cube. So we will find the volume occupied by all these particles, right, in BCC structure, and the volume of this cube, right? So now let's do a little mathematics. This is the right angle triangle. What we will do is we'll first find the value of this face diagonal AC and this body diagonal AD, right? So we will consider, to find this AC face diagonal, we will consider this triangle ABC, right? In triangle ABC, we have, if this is your right angle triangle, we have AC square is equals to AB square plus BC square. Therefore AC is equals to under root AB square plus BC square, right, which is AC is equals to, now we know that AB is the side of the cube, BC is the side of the cube, right? So this would be, this is your A and this is your A, right? If I put AB and BC, the value of AB and BC, we will get A square plus A square. This is under root 2A, right? And this is your AC. This is the value of the face diagonal. And to find the value of this body diagonal, we will consider this bigger triangle, right? And we will consider this at right angle. So therefore applying Pythagoras in this triangle ACD. In triangle ACD, we have this AD square is equals to AC square plus CD square. Therefore, AD is equals to this AC square, right? The AC square would be, what would be the value of your this AC square? This AC square, this is your phase diagonal. We have calculated it in this above. AC is equals to under root 2a plus CD. CD is this, which is your a square, right? So this is your AC square. AC square would be, from here you can find AC square is equals to 2a square. So AC square is your, C square is equals to 2a square plus a square. This CD, this is the length of the cube, edge of the cube. So this is your under root 3a. Right now we have the values of phase diagonal and body diagonal. Body diagonal is AD under root 3a, phase diagonal is under root 2a. Right now, volume of unit cell is a cube, right? A cube. Now we will just look at this, right? AD. AD is, you have one particle here, one is at the center and one particle at this corner. So two particles at corners A and D and one particle at the center. And we know that this center, the particle at the center is touching the four neighboring particles, right? So it would be like this, this and this, right? This is how it will look like if you look at the space filling structure. This is your A, this is your D, and this is the particle at the center, right? I'm again repeating. These A and D represents particle at the corner A and D, and this center C represents the particle at the center, right? And we know that the radius of the sphere is R. Here also this is R, here also this is R. So this entire length would be AD. AD would be equal to 4R, right? Now the value of AD is under root 3a, right? Therefore, since we know that AD is equals to under root 3a, right, from here AD would be 4R is equals to under root 3a. Therefore, a is equals to 4R upon root 3. This is the value of the edge or the length of the cube, the side of the cube, not the length, the side of the cube. And we know that volume of cube is equals to side cube, a cube, which is your 4 cube r cube upon 3 root 3, right? This will come out to be 64r cube upon 3 root 3, right? This is the volume of the cube, right? Now we have to find the volume of these particles, which will give us the space occupied by the particles at the 8 corners and the one particle which is at the center of the cube. So the total particle would be, we have already understood this in the previous lecture, that if particles are present, 8 particles at the corners would contribute one total particle, because at corner only 1/8th particle belong to this unit cell, and we have other neighboring unit cells as well, right? So to each unit cell 1/8th of the particle belongs, right? So to this unit cell And to find the number of particles, 1 upon 8th of this particle belong to every corner, and we have 8 corners, right, plus 1 particle at the center, and this particle is not shared by any other unit cell. So we have 1 plus 1, we have 2 particles for BCC, body cubic centered structure, right. So the volume of sphere would be volume. We know that volume of sphere is 4 by 3 pi r cube, right. Volume of sphere is 4 by 3 pi r cube. So total volume would be, due to in body centered cubic, we found that we have 2 particles, right, and the volume occupied or the space occupied by particles in BCC would be due to these 2 particles, and volume of one particle would be 4 by 3 pi r cube since it's a sphere. So volume of 2 particles would be 2 into 4 by 3 pi r cube, right. So it would be 2 into 4 by 3 pi r cube, which would be 8 by 3 pi r cube. Now we have the volume. If you put it in this formula, volume of sphere would be packing efficiency. Packing efficiency would be equal to volume of sphere, which would be 8 by 3 pi r cube, right, and you have volume of cube would be volume of cube we have calculated to be 64 upon 3 r cube, right, 2 3. So r and r will get cancelled, 3 by 3, 8 is 64, right. So what you get is pi. If you take this pi root 3 upon 8, right, this is the packaging efficiency in case of BCC, and this will come out to be 6.68. this is come out to be 6.68. So percentage efficiency, percentage of packaging efficiency would be 68%. This is 0.68. I'm sorry. This is your. This is 0.68. So percentage packaging efficiency would be multiplied by 100. 0.68. You will get 68%. Right. So for BCC, packaging efficiency is 68%. Right. So now we know for all the 3 structures, simple cubic, face centered and body centered, right, packaging efficiency is maximum for face centered, right. Let's write it over here. Packaging efficiency for simple cubic is 52.4%. packaging efficiency for FCC was 74%, and if you remember, this is same for packaging efficiency for cubic closed packing is same as FCC, and the packaging efficiency for hexagonal closed packing is same as cubical closed packing. So for FCC, cubical closed packing, and HCP, it's 74%, right, and for BCC now we know it's 68%, right. So the most efficient packing of particles is in face centered cubic, right, and HCP and CCP, because it's 74% same, right. So by this what we understand is that the solids, right, that crystallize in face centered cubic have maximum density and they have maximum incompressibility, right. So the example of particles that crystallize in FCC, in CCP or HCP is iron, nickel, copper, right. all these we know are denser, they have high density, right, because they have high packaging efficiency. And if you talk about particles like solids like sodium, potassium, all these crystallize in BCC, body centered cubic. That is why they are soft metals, because packaging efficiency is less, we have more open space. More open space means these are less denser, right? So that is why these BCC solids that crystallize in BCC structure have less packaging efficiency, so they are soft metals. Whereas particles or solids that crystallize in face centered cubic, they have high packaging efficiency, so they are more denser, right? I hope all this is clear. Thanks.